Sheet bending transforms flat metal into precise curves, using press brakes and roll formers to manufacture robust shells for industrial storage tanks. The prepared steel plate is now transferred to the Hoistler 3-roll bending machine. Using overhead cranes, the heavy plate is carefully positioned between the upper and lower rollers. Precise alignment is essential, because even a small deviation would affect the roundness of the final shell. Once the plate is centered, the machine clamps it firmly, and the rolling process can begin. The top roll presses the plate downward, while the two lower rolls move in a controlled manner, gradually forcing the steel to curve. Instead of bending the plate in a single pass, the Hoistler system applies force progressively. With each rotation of the rolls, the curvature increases, allowing the thick steel to be shaped smoothly without introducing internal stresses or distortions. For this operation, the plate is rolled until it reaches an outside diameter of 2.076 millimeters, forming a perfectly cylindrical shell. During rolling, the operator constantly monitors the plate position and the pressure applied by the rolls. Adjustments are made in real time to maintain uniform curvature along the full length of the shell. Because of the enormous forces involved, the rigidity of the machine and its foundation is crucial, ensuring that all bending energy is transferred directly into the steel. Once the desired diameter has been achieved, the rolled shell is carefully released from the machine and transferred to the welding station. Here, the longitudinal seam, where the two edges of the plate meet, is welded using the submerged arc welding process. This highly productive method is chosen for its deep penetration and high deposition rate. Two filler wires are fed simultaneously into the weld joint, allowing the seam to be filled rapidly while maintaining excellent mechanical strength. A layer of welding flux powder covers the molten weld pool, protecting it from oxidation and contamination. This also stabilizes the arc and improves weld quality. After solidification, the excess flux is collected and reused, making the process efficient and economical. The result is a strong, uniform weld seam that securely joins the shell into a single rigid cylinder. In addition to rolling, large steel plates are also shaped on a powerful press brake. A stainless steel plate measuring 60 millimeters in thickness and 7.2 meters in length is placed into the machine. With a bending capacity of 3,000 tons over 8 meters and a force of 800 tons per meter, the press brake applies controlled pressure along the plate, forming it into a precise radius. This process allows thick material to be curved accurately for special components that cannot be produced by rolling alone. The film then shows one of the most extreme forming operations. A steel plate weighing 43 tons, with a thickness of 150 millimeters and a width of 230 millimeters, is fed into the Hoistler rolling machine. Because of its enormous stiffness, the plate requires multiple passes under massive pressure. Slowly, the rolls force the steel to curve until it reaches a final diameter of 5,000 millimeters. Each pass brings the plate closer to its final shape, while the operator carefully controls roll positions to ensure an even, circular geometry. The operation begins when the worker carefully lifts the large, steel, dish-shaped workpiece and places it onto the central support of the Faxon automatic flanging machine. The component is positioned so that its open rim is perfectly aligned with the forming rollers. Precise positioning is essential, because the machine will shape the edge of the part into a uniform flange that must meet strict dimensional tolerances. Once the flange blank is correctly seated, the operator activates the clamping system. The machine firmly locks the workpiece in place, preventing any movement during rotation. After this, the forming head, which carries several heavy-duty rollers, moves toward the rim of the steel part. The machine then starts rotating the workpiece at a controlled speed, allowing the rollers to make smooth and continuous contact with the edge. As the rollers press against the rim, they gradually bend the steel outward. This forming action is not done in a single pass. Instead, the rollers apply increasing pressure step by step. With every rotation, the edge is pushed further into the desired flange profile. The automatic control system ensures that the force, feed rate, and angle of the rollers remain constant, producing a flange that is even all the way around. Throughout the process, the worker monitors the operation, checking alignment and surface quality. When the target flange shape is achieved, the rollers retract, the rotation stops, and the finished flanged component is ready to be removed for the next production stage. The steel plate is already positioned between the three rolls, and the bending process begins as the upper roll moves downward to apply pressure. The two lower rolls support the heavy plate, while the upper roll presses it from above, forcing the thick steel to start deforming. With a powerful hydraulic pressing force of 896 tons, the plate is squeezed firmly between the rolls, allowing plastic deformation to occur even in material up to 70 millimeters thick. As the rolls start rotating, the plate is pulled forward. While moving through the three-roll arrangement, the steel gradually takes on a curved shape. The bending is not done in a single step. Instead, the operator controls the downward movement of the upper roll in small increments. Each adjustment increases the curvature slightly, ensuring the plate bends smoothly without cracking or creating internal stress. As the plate passes through the rolls, its leading edge becomes curved first, followed by the middle and trailing sections. Because the plate is 500 millimeters wide, maintaining even pressure across the full width is critical. The rigid frame of the Daito bending roller keeps all three rolls perfectly aligned, so the curvature remains consistent from one side of the plate to the other. After the first rolling pass, the plate is fed back through the machine. The upper roll is lowered again to increase the bending radius. This multiple pass method allows precise control over the final shape, especially when forming thick and heavy plates. Each pass adds more curvature until the target diameter is reached. To avoid flat ends, the plate is often repositioned so that both edges can be pre-bent. By carefully adjusting the roll positions, the machine ensures that the ends are curved to match the center section. This creates a uniform cylindrical or conical form, depending on the production requirement. Throughout the operation, the rotation speed and pressing force are continuously monitored. The combination of high torque and massive hydraulic force allows the machine to bend extremely thick plates while maintaining a smooth surface finish. Once the desired curvature is achieved, the rolls are opened slightly, and the fully formed steel plate is released. It is then lifted away for the next stage of fabrication, ready to be welded into large pipes, pressure vessels, or heavy steel structures. The steel plate is first positioned in the 4-roll plate rolling machine, where the top roll and the 2 side rolls grip it while the bottom roll provides the driving force. At this stage, pinching is a very important point for cone bending. The operator must make sure not to pinch the plate too tightly. Practically, the minor diameter side of the cone should remain slightly looser than the major side, because this difference in grip allows the material to flow into a conical shape rather than a simple cylinder. To begin shaping, pre-bending is carried out on the first edge. The side roll on the minor diameter side is tilted upward, creating a different bending angle compared with the major side. After the rolls start rotating, the plate is pulled through the machine and the first edge is gradually curved. This pre-bending is achieved after rotating the rolls, so the leading edge already starts to follow the required cone profile instead of staying flat. Once the first edge is formed, the plate is stopped, and both the minor and major diameters are checked using radius templates. These templates ensure that the 2 sides match the designed cone geometry. If needed, small adjustments are made by slightly changing the roll positions before moving on. Next, pre-bending on the second edge is performed. The plate is rotated or repositioned so the opposite edge enters the working zone. The previous steps are repeated again. The side roll is tilted, the rolls rotate, and the second edge is curved to match the first. Again, the radii on both the minor and major sides are verified with templates to maintain accuracy. After both edges are pre-bent, the plate is repositioned at the center point of the machine. At this stage, both side rolls are raised and tilted up to equal positions relative to the top roll. With this symmetrical but inclined setup, the machine begins the main rolling phase. The bending process is repeated in multiple passes, gradually tightening the curve as the plate travels back and forth through the rolls until a smooth and continuous conical shape is obtained. Finally, if the cone is later welded and slight distortions appear, calibration can be applied after welding. By running the cone back through the rolls with light pressure, the final dimensions and roundness are corrected, ensuring the finished cone meets the required specifications. The flanging operation starts with a large dished end that has an inside diameter of 4.5 meters before flanging. The dish is positioned vertically on the rotating table of the fat cushion flanging machine. Hydraulic supports and centering devices hold the part firmly in place so the rim remains perfectly aligned during rotation. Once the dish begins to rotate, the flanging roller is moved toward the outer edge. The roller is mounted on a powerful hydraulic arm that controls both the radial pressure and the forming angle. As the edge of the dished end comes into contact with the roller, the material is gradually bent downward. This is not done in a single heavy pass. Instead, the roller applies progressive pressure, while the dish continues to rotate, allowing the metal to flow smoothly and evenly. With each revolution, the roller advances slightly, increasing the bending angle of the rim. This controlled movement prevents local stress, wrinkling, or cracking of the steel. The continuous rotation ensures that the forming force is distributed uniformly around the full circumference, producing a flange with the same height and thickness at every point. During the process, the operator closely monitors the forming zone. Small adjustments are made to the roller position and hydraulic pressure to keep the flange profile consistent and to maintain the required inside diameter. The steady rotation also helps maintain roundness, as the edge is transformed into a vertical flange. As the flange reaches its final shape, the roller makes a final smoothing pass to refine the surface and ensure the edge is straight and even. After the target geometry is achieved, the roller is withdrawn from the workpiece. The dished end continues to rotate briefly, allowing the operator to inspect the flange for uniformity. Finally, the rotation is stopped and the fully flanged dished end is ready to be removed, now prepared for welding and assembly into pressure vessels or large industrial tanks. A forklift is used to transport the red-hot steel plate from the heating furnace to the hot forming press. The operator carefully lifts the glowing plate and moves it slowly across the workshop floor, making sure the material stays balanced and does not lose its alignment. Because the steel is at extremely high temperature, precise handling is essential to prevent deformation or accidental damage before forming begins. Once the forklift reaches the press, the heated plate is gently positioned above the forming die and then carefully lowered onto the press bed. After the steel blank is placed correctly, the hot forming press is activated. The upper ram of the press begins to descend in a controlled manner, applying a massive vertical force onto the softened steel. As the ram moves downward, the steel plate gradually starts to bend and stretch, flowing into the shape of the lower die. Due to the combination of heat and pressure, the metal can be formed into deep and smooth curves without cracking. This process allows the flat plate to be transformed into a dished head or tank end used for pressure vessels. Meanwhile, the press continues, applying steady pressure to ensure the thickness of the material remains as uniform as possible. The forming dies guide the metal so that the curvature of the head is accurate and symmetrical. This is especially important for vessel heads, which must withstand internal pressure and therefore require precise geometry and structural consistency. Throughout the cycle, operators monitor the press to make sure the forming force and stroke remain within the required limits. Once the desired shape has been achieved, the upper ram slowly retracts, leaving the newly formed component resting on the lower die. At this stage, the tank head or dish head is still glowing hot. Using lifting equipment, the operators then carefully remove the formed piece from the hot forming press, completing the pressing operation. This flange forming and plate dishing machine is designed to shape thick steel plates with high precision and structural consistency. In the process, a flat steel plate is securely centered and clamped on a rotating table. As the table turns at a controlled speed, a powerful forming roller gradually presses against the plate surface. Under continuous pressure, the steel flows plastically, allowing the material to be smoothly formed into a curved or flanged profile without cutting or welding. The machine's rigid frame and hydraulic control system ensure stable force distribution, which is essential when forming plates up to 16 millimeters thick. Operators carefully monitor alignment and pressure throughout the operation to achieve uniform thickness and accurate geometry. This forming method improves material strength by maintaining continuous grain structure and reducing internal stresses. As a result, the finished flanged or dished steel component meets demanding industrial requirements for pressure vessels, tanks, and heavy structural applications. The flanging process begins with positioning a pre-cut steel plate onto the flanging machine's support fixture. A central forming die supports the plate from below, while hardened flanging rollers press against the plate edge. As the plate slowly rotates, controlled hydraulic pressure forces the rollers to bend the outer edge downward along the die profile. This gradual, continuous deformation forms a uniform flange without cracking the material. The operator adjusts roller pressure and angle to maintain consistent thickness and curvature throughout the process. The operation continues until the required flange height and radius are achieved. This formed flange allows the tank bottom to be welded accurately to the shell, ensuring structural strength, leak resistance, and reliable performance in storage tanks and boilers. The manufacturing process of an industrial steel vessel head begins with a flat steel disc prepared to precise dimensional and material specifications. First, the disc is carefully set onto the manipulator, which allows controlled handling of the heavy workpiece and accurate positioning throughout the forming stages. Using the manipulator, the disc is then transferred and finally aligned on the dishing press, where correct centering and clamping are verified before forming begins. Once the setup is complete, the dishing process starts. Under high forming force, the press gradually shapes the flat disc into a curved, dome-like geometry. This controlled deformation ensures uniform thickness distribution and structural integrity across the vessel head. As the press reaches the programmed depth and curvature, the dishing operation is completed. The formed head is then released and removed from the dishing machine using the manipulator, preventing distortion or surface damage. After dishing, the process continues with flanging. The dished head is positioned on the flanging machine, where the edge is progressively bent outward to form the flange. This flange is essential for welding the head to the cylindrical shell of the pressure vessel. During flanging, the operator levels the head as necessary to maintain roundness and dimensional accuracy. Adjustments ensure that the flange angle and diameter meet strict engineering tolerances. When the flanging process is finished, the fully formed steel vessel head is removed from the flanging machine. At this stage, the head is ready for inspection, welding preparation, or further finishing operations, meeting the demanding requirements of industrial tanks, boilers, and pressure vessels. The welded beam manufacturing process begins with nesting, where steel plates are digitally arranged to optimize material usage. Dimensions for webs, flanges, and stiffeners are carefully calculated so that multiple components can be cut from a single plate with minimal waste. This step ensures efficient use of raw material and provides accurate data for subsequent cutting operations. Next is cutting, during which the nested layouts are transferred to CNC-controlled cutting machines, commonly using plasma, oxy-fuel, or laser technology depending on plate thickness. The steel plates are cut into individual components, such as web plates and flange plates, according to precise dimensions. Accurate cutting is critical, as it directly affects alignment and weld quality in later stages. After cutting, the components undergo grinding. All cut edges are cleaned to remove slag, burrs, and surface irregularities created during thermal cutting. Grinding also improves edge smoothness and prepares the surfaces for welding by ensuring proper weld penetration and reducing the risk of defects. Clean, uniform edges are especially important at joint areas. The process then moves to tack welding. The web and flange plates are positioned in the correct orientation using fixtures or alignment jigs. Small temporary welds are applied at specific intervals to hold the components firmly in place. Tack welding ensures that the beam maintains correct geometry during handling and full welding, preventing misalignment caused by heat distortion. Following tack welding is copping. In this stage, specific sections of the web or flange are cut or shaped to allow proper fitment with other structural elements, such as columns, brackets, or connections. Copping may involve trimming corners, cutting notches, or creating clearance for weld seams. This step ensures compatibility with structural design requirements. The main structural joining occurs during welding. Continuous welds are applied along the interfaces between the web and flanges, typically using automated submerged arc welding or other high-deposition welding processes. Welding parameters such as current, voltage, and travel speed are controlled to achieve consistent weld penetration and strength. As welding generates significant heat, the sequence is carefully managed to reduce residual stresses and distortion. Once welding is complete, the beam proceeds to gauging. Dimensional checks are performed to verify flange spacing, web alignment, straightness, and overall beam geometry. Measuring tools and gauges are used to compare the actual dimensions with design specifications. Any deviations identified at this stage determine whether corrective actions are required. If distortion is detected, the beam undergoes straightening. Mechanical presses or hydraulic straightening machines are used to correct bending, twisting, or warping caused by welding heat. The straightening process is carried out gradually and precisely to avoid introducing new stresses or damaging welds. Proper straightness is essential for structural performance and ease of installation on site. The final stage is final inspection. The welded beam is thoroughly examined for dimensional accuracy, weld quality, and surface condition. Visual inspections check for weld continuity, cracks, undercut, or spatter. Depending on project requirements, non-destructive testing methods such as ultrasonic or magnetic particle inspection may be applied. Only beams that meet all technical and quality standards are approved for further finishing, storage, or delivery. Through these controlled and sequential steps, a welded beam is produced with the required strength, accuracy, and reliability for structural applications. The process begins with thick steel slabs being charged into 4 reheating furnaces, where they are uniformly heated to approximately 250 degrees Celsius. This step ensures the steel reaches the plastic state required for intensive deformation. The furnaces operate continuously and supply hot slabs to the rolling line, consuming energy equivalent to that used annually by around 200,000 households. Once heated, each slab passes through a stouch press, edging press, with a pressing force of up to 200 tons. The press reduces the slab width by as much as 300 millimeters. This operation improves dimensional accuracy and optimizes the material distribution before rolling. The slab then enters the roughing mill, Vorstrasse. Driven by 2 motors with a combined power of 2 times 20 megawatts, the mill applies rolling forces of up to 500 tons. In several passes, the slab thickness is reduced dramatically from about 250 millimeters to 45 millimeters, while its length increases significantly. After roughing, the steel strip moves directly into the finishing mill, Fertigstrasse. Each stand is powered by drives rated at 30 megawatts, around 40,000 horsepower. Here, the strip undergoes precise thickness control and is rolled down to its final gauge, ranging from 25 millimeters to as thin as 1.5 millimeters, with widths reaching 2.020 millimeter. At this stage, the strip can already be hundreds of meters long. The hot strip then passes through the cooling section, where controlled water cooling reduces its temperature from about 750 degrees Celsius down to 50 degrees Celsius. The cooling system handles approximately 100 million cubic meters of water per year, ensuring uniform mechanical properties along the entire length. Finally, the cooled strip is wound on a coiler, haspel. The finished coil can reach a width of 100 millimeters, a weight of up to 35 tons, and an impressive strip length of up to 1.5 kilometers, completing the transformation from a single steel slab into a continuous steel coil. Steel production begins with solid steel slabs being transported to the Einlaufstoßofen, or pusher furnace inlet. The slabs are fed one by one into the furnace using mechanical pushers. Inside the pusher furnace, the slabs are gradually heated in a controlled manner to achieve a uniform internal temperature suitable for further processing. The heating process is continuous, with new slabs pushing previously heated slabs forward through the furnace chamber. As the slabs move through the furnace, they are exposed to high temperatures that ensure proper plasticity of the steel. This heating stage is essential to reduce internal stresses and prepare the material for deformation. Combustion gases and heat are carefully regulated to maintain consistent thermal conditions throughout the furnace length. Once the slabs reach the required temperature, they exit through the Einlaufstoßofen, or pusher furnace outlet. At this point, the steel is fully heated and ready for mechanical processing. The hot slabs are transferred immediately to the next stage to minimize heat loss, ensuring efficient energy use and stable material properties. During heating, exhaust gases and airborne particles generated inside the furnace are directed to a washer or gas scrubber system. In the scrubber, the hot exhaust gases pass through a washing process where water captures dust, scale, and harmful emissions. This step reduces environmental impact and cleans the exhaust before it is released, while also protecting downstream equipment from contamination. After leaving the furnace, the heated slabs are guided toward a series of walzen or rolling rolls. These rolls apply high compressive forces to the hot steel, gradually reducing its thickness and shaping it into the desired form. The rolling process is carried out in multiple passes, with each set of rolls precisely adjusted to control thickness, width, and surface quality. As the steel passes through the rolling stands, scale formed during heating is partially removed, and the internal grain structure of the material is refined. The combination of high temperature and mechanical deformation improves strength, toughness, and dimensional accuracy. Roll speed and pressure are continuously monitored to ensure stable processing conditions. Throughout the entire process, material flow is synchronized between furnace operation, gas cleaning, and rolling stages. This coordination ensures continuous production, minimizes energy losses, and maintains consistent steel quality. The result is a precisely processed steel product ready for subsequent cooling, coiling, or further finishing operations.